So thank you guys. I'm Shalendra Katare once again with you, your host today. And we'll start from our yesterday's session where we were continuing a couple of topics like optimizers, loss function, and all those kind of things. And we also covered in detail what is learning rate and how to deal with it. So those topics are covered and they will be available in video. So this Sunday afternoon, we are going to take up a next topic, which is regularization of neural networks. So we have not only L1 and L2 regularization, so we have a couple of more methods of regularization like dropout methods and batch normalization. So we'll study everything today in details, and we'll after that we'll take up the questions. Okay, so we'll start today. And see, I just first refresher on overfitting, a refresher, I think, from machine learning lessons. I'm giving you one refresher. So just have a look at the, is screen visible?
Yes.
No, but is that complete screen visible?
No.
Okay, now is it visible, complete screen? Is complete screen visible now?
No, it is partly, it is video.
What? No, overfitting is what is regularization? Is that screen visible?
Yeah, it is visible.
Fully visible?
Yes.
Uddesh, can you see the screen?
Yes, sir.
Okay. So we will repeat what is regularization from our lessons of machine learning. So you see on the box on the left hand side of the PPT, and that's where I have made on the top. In the top row, I have made three figures. So there are some points which are arranged in curvilinear fashion. So if we fit a straight line to it, it will be a very simple model. So it will be underfitting because all the time it will be giving us the wrong results. So it is underfitting. And see the extreme right. And if we try to pass our curve from every point where it's zigzag curve, from each and every point, so that will be overfitting. Why? Because for that particular curve, it will give the right results, 100% right results. But if we just go outside the curve and any unseen data, if you put inside that model equation, it will completely doom off, like it will give very wrong results. Maybe below 50%, below 60%, like that it will give. So this is overfitting. So what is right then? So what is right is what is shown in the middle. So we have a very humble curve, which is a degree 2 curve, which is passing from in between the points. So that is the kind of curve fitment we want, which is we say just right. It is a generalized curve. Okay, that's what we want. So now when we plot model complexity with error means total error given by the model. Total error given by the model, when we plot it against model complexity, we see that as our model becomes complex and complex, so your training accuracy will go on increasing, but your testing accuracy beyond a point, it will deviate from your training accuracy, as you can see from the plot, which is in the second half of that box on the left hand side, right? So I have titled it as training versus testing error. Okay, so there is a like after a point, the gap between testing error and training error and test error widens and goes on increasing. So that's where we predict that is something overfitting is happening. So how to remove overfitting? So overfitting can be removed by we want a model with just right complexity. It not be too model equation should not be too simple, and model equation should not be too complex, not too complex. We want just right, neither simple model, not very complex model. We want a right complexity model, which optimum model we want. Okay. So now that's what is the bit theory with what everybody learns in machine learning, and you might still be remembering. So if you see your top three, on the top half there are three curves, which you see a straight line and a zigzag curve and a just right curve. If you see that, So underfitting, whatever I have marked as underfitting is a very simple straight line. It is a very simple equation. And whatever I have marked as overfitting, that is nothing but a very high degree polynomial, maybe degree 4, degree 5. And just right equation, what we have marked, which is our which is our optimum result. So that is nothing but a degree 2 polynomial. So that's how we are looking at our model complexity. Okay. So now that is the theory. Okay, theory it is okay. Now what do you want? As a practitioner, you are facing a problem of overfitting. What to do then? Well, you want an optimum model, but how to get that optimum model? You are getting a overfitting. Okay, so we are getting a training error and test error, which are very wide apart. So you want something which is an optimum model. So how to get it? So right now you are in the situation of overfitting. So how to get it? So that's also a very nice solution we learn in the case of machine learning. We add a regularization term to the machine learning equation. Whatever is your original machine learning equation, whether it is a straight line or degree 2 curve, whatever. So we add a regularization term. It is an error term. We introduce extra error into that machine learning model. And why we do so? By increasing that extra error, we increase the bias of that model. We increase bias of that model, and we try to reduce the complexity of the overall machine learning model. Okay. So how does that work? So let us get into a little more detail. So like this was in the case of say polynomial regression, we are getting this kind of generalized simple case. So if we generalize little more in case of neural networks, first of all, you see the right hand side column on the left. Diagram is divided into two parts. Right half is the complete text written and left half complete pictures are given. So in the pictures, you see the plot, which is in the second column, middle column. You go to the middle column, where we have three plots. So we have some data which is plus and zero. So you see that some plus are intermingled with some plus are intermingled with the zero class. So plus say if red class with plus is a negative class and zero is positive class. So some two negative points are intermingling with the positive class. So whatever is the called overfitting. So see what is the kind of curve we have. So it is like it is doing a perfect separation, but it is very complex curve. Okay. So if we give some kind of unseen data to this kind of model, the accuracy will be very less because it is overfitting right now. Then you come to the middle one. Middle one is a simple straight line which is separating plus and zeros. But you see there are it is making a lot of errors. It is making a lot of errors. A lot of plus are on the say right hand side of the line, and lot of zeros are there on the left hand side of the line. So it is a suboptimal model. So it is nothing but your more bias is there in this model. So this is called underfitting. So what is the just right curve? So just right curve also we have shown here just in that the bottommost middle in the middle column. You just see the bottom figure, which is I have marked as appropriate fitting. So appropriate fitting is a simple kind of a simple curve, which is making a simple curve, maybe 2 degree polynomial, degree 2 again. So it is making two errors like 2 plus, which is plus 2 plus are classified with zeros. So we are living with certain errors, but we are making certain errors. True, we are accepting certain error, but what we are getting in return? In return, we are getting a very generalized model, a very simple curve we are getting, which is clearly separating plus with zeros, right? Plus with dot, plus and dots are clearly separated with a simple model. And it is yet making two errors. We see that it is making errors. So we have to live with those kind of errors. So this is the generalized principle of overfitting, which applies to neural network as well. Because your neural network ultimately does what? Neural network also is classified into two categories. Either classification, it will do either classification or it will do regression. So right now we are talking about the classification case. So right now said so if there is only one node in the output layer, that means there are only two classes. So we have this kind of, and it can be plotted along 2 dimensions. So we are discussing this case with a neural network. Okay. So neural network, with neural networks, we are giving it a little bit generalization. But if you see the curves and the concept remain the same, whether it was a polynomial regression, simple polynomial regression, or whether it is a simple classification. The concept remains the same. Only the network is different here. Here it was simple polynomial regressor, and here it is a complex neural network. So it is little generalization we are doing. So let us get into like a little more detail. So we do something called a regularization. So suppose your model is in the under the category of overfitting. In training data, it is doing very good results, and in testing data, the results are not that good. So maybe result difference between training error and testing error, training accuracy and testing accuracy is more than 10%, more than 15%. So we say that model is overfitting. So now you are under the condition that your model is overfitting. So what you do? So as we discussed some time back, we add a regularization term. Regularization term means in machine learning, we know that the equation of that say regression. So like in beta coefficients, we add an error term. So what that does, it penalizes the coefficients. It penalizes the coefficients. So it forces coefficients of linear regression model to reduce from large value towards smaller values. Okay, and so similar. Suppose in case of linear regression, it penalizes coefficients, beta coefficients. So what is its parallel in deep learning? It's parallel in deep learning it weights and biases. So if we apply a regularization term to a deep learning model, it reduces the magnitude of weights and biases. Suppose weights and magnitudes were going in thousands. So by applying a regularization term, maybe it is possible that it may come under 100 or under 10. So a less value of weight and bias is always considered better in neural networks. Okay. Similarly, the beta coefficients also. We do scaling and all to reduce the overall magnitude of the beta coefficients. Okay. Now there are two types of regularization we are discussing here. In one kind of so we'll discuss in later. So this is the difference between linear regression and your neural network. In linear regression, the regularization term reduces the beta coefficient values, and similarly in the neural network, your regularization term, if added to the model, it reduces the value of weights and biases. Because weights and biases are nothing but parallel to your beta coefficients of linear regression. Okay, they are parallel. Both are parallel here. Both are trainable parameter. Weights and biases are also trainable parameters, and beta coefficients are also trainable parameters. Got it? So now see how regularization works. So when we work with a cost function, so you see expression in the middle on the right hand side of there are two terms. So first is our regular loss function, which we work regular loss function, right? Like your mean squared error and all that. In the case of linear regression, suppose you are working with mean squared error. So that is your regular loss function. Or in case of a classification, you are working with binary cross entropy. So here loss function they have shown here is binary cross entropy. So it is a classification case with two classes. So to reduce overfitting, as I said, we add a regularization term. So we have added a regularization term. So let us see how it looks like mathematically. So mathematically, like it looks like very similar to what you do in linear regression. So in cost function in L2 terms, we have regular cost function. You see the equation of cost function on the top. L2. What is L2? What is L2 means loss plus lambda upon 2m plus sigma of weight square. So whatever weights you have, suppose you have 100 weights. So this is a weight matrix with all weights. You will do square editor and do a sigma of that across those weights. And another scheme we have is the L1 regularization, in which you don't do square of the weight matrices. What you do? You simply add up the weight matrices. Lambda upon 2m remains the same. and lambda upon 2m remains the same, and weight matrices are added as it is without any squaring. In L2, you square and add it. So now what difference does it make? So first let us discuss L2. So what it does, L2 reduces the weight towards zero. Weight values, suppose weight values are large in thousands. So the weight value will weight value of some of the weight will become near to zero. It will not become zero, maybe 0.001, 0.001, but it will not be zero in case of L2. But in case of L1, what will happen? Totally some of the weights will reduce to zero. Okay. So some of the weight will be reduced to zero. So what is the meaning of some weights being zero? If we have more weight means complex model, and some weights are reduced to zero means the model is less complex, because some weights are zero, those neurons will not be considered, right? So you have less complex model. That's what you wanted, right? That's what you wanted, right? So in case of L1 regularization, some weights are getting reduced totally to zero. So some weights will be eliminated. So some neurons will also be eliminated. So your model, suppose, is right now made up with 1000 neurons. Maybe if you apply L1 regularization, maybe say 200 weights are becoming zero. So 200 neuron connections are getting eliminated. So your model is simplified from 1000 trainable parameter to 800 trainable parameter. So you have simplified the model. So this will reduce overfitting, right? Because we have seen that if complexity of model reduces, overfitting also reduces. Okay. And in case of L2 regularization, weights will tend to become 0, 0.001, 0.001, 0.0001, but they will never exactly become 0. They will never exactly become 0. Okay, so this is the difference between L1 and L2. So in which lambda upon 2m, so lambda is nothing but your regularization hyperparameter. Regularization hyperparameter. And what is m, that I'll tell you little later. So lambda is your regularization hyperparameter, which you adjust by say by say grid search, or some similar grid search, random search, or some similar random hyperparameter optimization method you have to use to get the exact value of lambda. By trial and error also you can get. So trial and error, or it is manual method, is very crude. So you can either go for grid search, or you can go for random search, or Bayesian search, or multi-fidelity search, or there are genetic algorithms. There are so many optimizers available to tune the hyperparameter. So you have to use one of the hyperparameter tuner to get the value of lambda. About 2m we'll discuss little later. Okay. So difference between L2 and L1 is understood. It is exactly same as in the linear regression. Linear regression, L2 we call as Ritz regression. Ritz regression we do square of all beta coefficient, add it up. Here we do square of all weight matrices, will square it up and add it up. And L1 is called lasso, or L1 is called lasso, in which we never square up, we just add it up as it is. So it is exactly same. Concept is exactly same. And in there also in lasso, beta coefficient become 0. And in Ritz, beta coefficient become near to 0, but they never become 0. L2 in linear regression also, they become near to 0 but never become 0. L1 which is lasso, so in lasso they become 0. They'll become to 0. So suppose you want to eliminate some beta coefficients from a linear regression equation. So better to use unnecessary, suppose you want to eliminate some unnecessary features. So better to use lasso. Better to use lasso, so that some beta coefficients are becoming 0. So automatically those features are getting eliminated from the equation. So what is the downside of it? So downside of it is like that L2 is computationally more expensive than L1. L2 is computationally more expensive than L1, both in linear regression and in neural networks. Now you will ask me, like, there are two schemes available, L2 and L1, which one to go for? So generally, like for some reason, like by default, people use L2. By default, people go for L2. That's what it is. Like most of the cases, like very big scientists like Andrew Ng and all that. I have read about some articles from Andrew Ng. So he tells that by default I use L2, And suppose L2, your results are not good, as well you can try with L1. Now see on the right hand side. In practice, we usually prefer L2 over L1. That is what is the practice. Okay. Now you just see the code here. From Keras, just see code on the right hand side, which is the black box. It is written from Keras, import regularizer, model.add. This is the dense layer we are defining with 64 neurons. And input dimension as 64. Kernel regularization, we are using regularizer.L2. Regularizer.L2. And in the L2, we are giving the value of lambda.
We are
Lambda
at
is
previous
0.01.
slide only. Actually.
Pardon?
We are at slide number, previous slide only.
You are not at L1 and L2 slide? You are at which slide? Can you see L2 and L1?
Yeah.
No, sir.
That's where we are. No? That's where we are. Okay. So you can see L2, L1, right?
Yes. Yeah.
So that's where we are. So in bracket, we are giving the value of lambda, which is 0.01 right now. And about the magnitude of lambda, we'll discuss little later. Okay. So lambda is given in, so this is how we define the regularization in the code. In code, it is very simple. Just define the value, just define regularizer dot L2. It will take L2 regularizer, and 0.01 lambda value, it will take 0.01. So 0.01 is a hyperparameter. So you have to use 0.02, 3, 4, whatever. And you have to optimize, you have to adjust it for lambda. So that's what you have to vary. Okay. So you can vary lambda with the help of grid optimizer or random search or Bayesian search, as I said earlier. So it is, so this is the story of L1 and L2. Concept is exactly same as simple machine learning. What we learn in machine learning, concept is simple, exactly same. So instead in machine learning, L1 and L2 penalize your machine learning, they penalize the beta coefficients in case of linear regression. But in case of neural networks, they penalize weights and biases. Similarly, because parallel, their beta coefficients are the trainable parameters, and here in neural network, trainable parameters are weights and biases. So here, regularization term, if you add to a model equation, it will penalize weights and biases. That's what our, so this is the story. So I'll take a minute break. So now we are going to another concept of regularization, which is dropout regulation. This concept is not there in machine learning. This concept is very new to neural network. So I stop for a minute and call out for questions if you have any till this point.
I think we are good.
You're good, Dr. and Soman?
Yes, sir. Yeah.
It's simple, right? Same, exactly same as the linear regression, lasso and reads. So no difference. Okay, so now we are getting to a new second concept of regularization, which is dropout regularization. So dropout regularization again is very simple. You see a standard neural network model given. See, left hand side, there are two figures, A and B. So one is standard neural network, which is densely connected. Each neuron is connected to every other neuron in the next layer. Understood? It's a dense layer, simple dense layer of a NN. Is a NN model I'm showing. And in the output layer, there is only one neuron. So it is a classification model, two-class classification model I've shown here. So each neuron in one layer is connected to every other neuron in the next layer. That's what your simple ANN model, artificial neural network model. Okay, very good, well and good. So this is your simple neural network model. And it is having some kind of complexity. So say how many, can you count, Soman, how many neurons we are having in that figure which is titled as A? How many neurons we are having?
So 15 and a final output one.
60 neurons, right? So there is some level of complexity in this ANN model. Agreed? Some level of complexity is there. Now, if I come to the right hand side, which is B, whatever is crossed, I have removed them. I shut them off by making their weights as 0. I have shut off this neuron. I have removed them from the model. So how many are remaining, Dr. Shailesh? How many are active now?
1, 2, 3, 4, 5, 6, 7, 8 plus 1.
8 neurons are remaining, right? So which is the simpler model? Model A or model B?
B.
B is simpler, right? So what you wanted? So suppose your model A was, in case, assume that your model, for a particular data set, model A if was overfitting, I want to simplify the model, means I want to reduce the trainable parameters. So that's what I did in model B, right? So model B is a simpler model. So it is likely that with right amount of neurons removed, I will have a simpler model. So it will not overfit. It may less overfit. So what is my catch here? My catch here is I am removing right now 2 and 2, 5 and 7. 7 neurons I am removing. So maybe with removing 7 neurons, it is a very underfitting model. So maybe that I have to remove only 4 neurons, 5 neurons, 3 neurons. That's where is my key, right? So I should know right amount of neurons which I have to shut off, which I have to remove. That's what I need to know to get the model of right complexity. And we know that the model of right complexity for a particular data set, it is specific to a data set. For a particular data set, it will not overfit. So this technique is called dropout regularization. Dropout means we are dropping out some neurons. So I think you understood it.
Yeah.
So
one question on this.
yeah.
So now, I have means after doing many hyperparameterization and all, I have finalized the standard neural network on left side, right?
Okay.
But when I am dropping out, then it will decrease the accuracy of the standard neural network. So it will be an issue.
Right now I already told you that the model A, which you finalize, it's already overfitting. Overfitting means what? It is giving a great accuracy on training data and very poor accuracy on testing data, right?
Yeah.
So you want a generalized model. So what will happen? So when you do generalized model, the accuracy on training data will little bit reduce, but accuracy on testing data will increase, and accuracy of test data and accuracy of trained data will be within plus minus 5%. That's what we want, right?
Okay. Yeah.
So that's where you have to compromise accuracy on training data set, which is reducing. You have to compromise that much for getting a general model. Okay. So now catch here is how many neurons I should remove. And these neurons, I'm telling you, they are removed randomly. We choose them randomly. And we do it during the training phase. Like when we do forward pass or backward pass. That time we do it shutting off neuron. We do it either with forward and backward pass. We do it at that time. At the training time we do it. And randomly we choose what kind of neurons we need to shut off. These are two important things. It is done at the time of training, number one, and which neuron you want to choose, it is chosen randomly. Okay, so that is one thing for this slide. Let us go again to the next slide. Now like why we shut off the neurons? What happens during the training in a fully connected network like I'm shown in the model A? What happens? There is some kind of localized interdependencies formed between the neurons. When we do training, some kind of local dependency is formed between the neurons. Some kind of local dependency is formed between the local dependency is formed. So we don't want that. We want all the neurons of a particular model to learn independently for more generalization. So if local dependency is developed, then there is a more chance of overfitting, and we don't want that kind of model. So what we want from our training, or each and every neuron of our model should learn independently. So suppose there is an interdependency between a particular cluster of neurons, which is formed during the training in a fully connected model. And if I switch off certain neurons randomly out of that cluster, so that interdependency will be removed, right? That interdependency will be removed, and the remaining neurons will tend to learn more independently. So that is what is the idea behind dropout layer. Okay. So that's what is the idea, main idea behind dropout layer. We don't want neurons to form clusters. In interdependency between the neurons is developed, and some kind of cluster is developed between the neurons. That's what we don't want. We want all the neurons to learn independently. So from that cluster independence, randomly we switch off some neurons. So automatically that interdependency is removed. Number of neurons are removed. Their connections are removed. So all the remaining neurons tend to learn independently. So that's what we want for a generalized kind of neural network. So that's what is the desired model. That's what is the idea being dropout. So let us see what next. There are certain rule of thumbs, like some rule or some main points which you have to remember while working with dropout layers. Like we learned some 8 points for learning rate. We learned 8 points what to do and what not to do for learning rate. 8 points we considered. Similarly, we have 6 points for neural networks. So first of all, I already told that dropout we do randomly so that there is no interdependency or no cluster is formed between the neuron, and all neurons learn independently. That is point number 1. Now, if you do dropout, say 0.2 dropout, 0.3 dropout, if you do, so it will increase your number of iterations to convergence. Like suppose previously your model A was taking 50 or 40 epoch to converge. With dropout, it may take 80, 60 or 80 more, almost double the number of double the number of epochs it may take. That's what is the experimental observation. So it may take double number of epochs to converge. But however, the training time for each epoch is less. Why it is less? Someone can you tell? With dropout, the training point for each epoch is less compared to the fully connected model. Why it is so?
Sir, because we do not have to calculate weights and biases for certain neurons.
Yeah, so it is simply because you have a simpler model, right? So simpler model, training and time also will be less. That is point number 2. Point number 2, suppose you have H hidden units. Okay. If you have H hidden units, each of which can be dropped. Suppose you have 10 neurons and train neurons in the model, output model you cannot drop. But out of these remaining 9 neurons, you can drop anything. So how many total models are possible? 2 to the power H models are possible. That's what is the number of models which are possible if you do this kind of random arrangement. That is point number 3. So you use as an empirical formula. If you have H hidden neurons, and each of which can be dropped independently, so total you can form 2 to the power H number of neurons. So this is a kind of empirical formula. Or simply you can work out, if you think little more in terms of permutation combination. If you think on those lines, I think you can work on 2 to the power H. But that is not important right now. Let us go to the point number 4. The probability of choosing how many nodes should be dropped is the hyperparameter. As I told, how many neurons should be dropped? Like here we have dropped 7 neurons. So how many neurons should be dropped? It is a hyperparameter. It is a hyperparameter there. So it is a hyperparameter of the dropout function. Dropout can be applied to both hidden layer as well as input layer. I think people have some misconception that dropout can be applied only on the hidden layers, not for the input layer. So, someone would you like to tell what are the implications if I apply dropout to input layers? What are the implications?
Sir, if we apply dropout to the input layer, it might cancel some of the features.
Yes.
Some of the features or input attributes might not get used at all.
And you may not want that. You may not want that.
Yeah.
In certain conditions, it is okay, but in certain under certain condition, you may not want feature to be dropped. So, and in those conditions, you apply dropout only to the hidden layer. And of course, output layer you cannot apply dropout because it is classes are calculated either one or number of equal to number of classes in your target class, right? So either 2, 3. That's where you cannot apply dropout. Of course, you cannot apply. Otherwise, all your model will go for a toss. So that is point number 5. Then point number 6, due to these reasons, dropout is usually preferred when we have a large network structure in order to introduce the randomness. Okay, so it is very, see, I'll read once again. Due to these reasons, dropout is generally preferred when we have a large neural network structure in order to reduce randomness. So if it is a small network of say 5-6 neurons, what kind of randomness you will introduce in that? So if your neural network is a large frame, large neural network, a very deep neural network, if you have, then you have some scope of introducing a good number of good randomness in that model. So it's a very obvious mathematical kind of very common sense point. If number of neurons are more, the possibility of randomness will be more. So dropout is generally preferred in large neural networks. Okay, that's where it is more effective. So these are the 6 points of neural networks. And let us see like what this layer wants to tell now. This particular slide, Python code, you can see probability of dropping this thing further to get result using the grid. See how to apply dropout. So you see model sequential. In the model sequential, dense layer is defined as usual. Activation, ReLU and all you defines the dense layer. Just next to the dense layer, just define a dropout layer called dropout 0.25. So you define dropout 0.25. 0.25 means 0.25 is the probability of dropping. Each neuron has 0.25 probability of dropping. That's what you have introduced here. Okay, so that's what, and this is to be, this 0.25 is not a magic number which come from air. This is a hyperparameter which you need to optimize using either grid search or say random search or Bayesian search or whatever optimizer hyperparameter tuner you are using. So using that you have to optimize this. So there are a few more things like why regularization reduces overfitting. I think we have understood very well why regularization reduces overfitting, because either if you apply L2 regularization, it will make your weight smaller. That's how it will reduce. And if you apply L1, it will altogether make it 0. So it will eliminate some neuron. It will make model simpler. So that's how it is. And regularization tunes the loss function by adding the penalty term. It prevents the excessive fluctuation of coefficients. So same thing we learn in regularization tunes the loss function by adding a penalty term. We have seen penalty term is nothing but your regularization term. That's what you add. And similar to machine learning, it prevents excessive fluctuation of coefficients. Excessive fluctuation of coefficient, it prevents at the time of optimization, minimization. Regularization attempts to reduce the variance of estimator by simplifying it. Something that will increase bias. So regularization will increase bias. Understood, na? So suppose in training data, your accuracy was 99%. If you introduce regularization, your testing accuracy will increase, but your training accuracy may go up to say 95, 96. So your accuracy is reducing. That means what? You are introducing bias in the model. Okay. So that's how these are the effects of introducing regularization, and we know very well that why it is why it reduces overfitting. Dr. Shailesh, would you like to repeat why it reduces overfitting?
Because it either decreases the weights to 0 or 10 to 0. So that's why.
Yeah, simply in simple term, let us use that. It simplifies the model.
Yeah, it simplifies.
Very simple. It simplifies the model. That's why it reduces overfitting. So then there are some practical tips. Dropout value 0.25 you have seen the last code. So one gentleman, very learned scientist, Dr. Joseph Brownlee is suggesting start with a value of 0.2 and end with 0.5 if you are doing manually. Start with 0.2 and end with 0.5. That's what he's telling is the good value. You play in between. And you always start with 0.2. That's what is the first tip. So if regularization is very less, say 0.1 or 0.01, instead of 0.2, if you are using 0.01 or 0.1, then it has minimal effect. Effect will be minimal. There will be very minimal effect. There will be, it is just, if you are using 0.01 as your dropout as 0.01, that is almost as putting there is no regularizer. There is no dropout. 0.01 is no dropout. And if you put very high like 0.9, so you are like almost shutting off, each neuron will have probability of 0.9, which is random probability to get dropped off. So it is a very high regularization. It is number 3. Dropout, use dropout on incoming layer. Incoming layer means input layer as well as hidden layer. Both layers we can apply. Both layers we can apply, but depending upon use case, in some cases, you may not want to apply dropout in the incoming layer because it shut it off, remove some features. Okay. Then use a large learning rate with a decay and a large momentum. See, it is something which you should object just now. Mr. Brownlee is telling use a large learning rate with a large momentum. That's what we learned. Learning rate and momentum should not be large at a time. If momentum is large, learning rate should be small. What this gentleman here is suggesting, use large learning rate with decay. Learning rate with decay. So this the decay can be linear or decay can be exponential. That's what we learned yesterday. So you use a large learning rate with decay. That's what he's suggesting, with a large momentum. That's what he's suggesting. It is contradicting to what we have learned yesterday. But what I suggest, we have to take Mr. Jason Brownlee very seriously. So I'm not, but I will still say that you use it and then you believe it. Like you do it and then believe it. He's telling like that, but instead of first you implement and then believe it, instead of blindly accepting it, because this teaching is contradicting with what we have learned yesterday. But it is still there, and it is told by a learner scientist. So if you are using large learning rate with a decay, with a large momentum, do it and then you decide whether you want to use it or not. That's what I suggest with this. So my recommendation is try yourself. Don't believe blindly. Okay. So that's what my recommendation with this. And last is something which is new, which we have not covered in our anywhere. We have not covered in. It is an advanced concept in neural networks. So if you are using a large learning rate, if you suppose you are following the last but one recommendation of Mr. Brownlee, and you are following a large learning rate. So if you are following a large learning rate, means you will get larger weights. You will get larger weights. Weight value will be larger. Magnitude of the weight will be larger. Absolute value of the weight will be larger. So in that case, what he is suggesting, you have to constrain the size of network weights. Means that magnitude, you have to constrain it to some value. You should not say allow it to go beyond say 100, 200, whatever is the optimum number. Say you should constrain it first. You should not allow the weight magnitude to grow beyond a number. And how to do that? It is something advanced science and generally not taught. But I am providing you here a resource by the same scientist, Mr. Brownlee. You see, it is called max norm regularization. So simply you have to put one more term, which is nothing but max norm normalization. So how to constrain weight, I am not discussing it today. I will suggest you to go through this article, which is shared with you, and it is on the bottommost part of this PPT. It is shared already with you. So in this article, he has given the theory, how to use that constraint the weights, and he has also given the code, which part of the code you need to use in your actual Jupyter files to constrain the weights if you are using large learning rates. So these are all trial and error things, and I don't think I need to cover each and everything in the class, because if you see this article within 5 minutes, you will be able to learn how to do that. Okay, some things to be left for the learners as well. So this max norm regularizer. So max norm regularization is for what? It is to constrain the magnitude of weights. And how it is done? Please refer to this article which I have mentioned in this particular PPT. Then that regularization summary. Regularization summary, we have to remember that if your weight value is large or if your model is complex, you will tend to go for overfitting. So you have to reduce the value or magnitude of the weights or beta coefficients value you have to reduce. Okay, you have to reduce that to avoid overfitting. Smaller weights lead to simpler models, which in results helps in avoiding overfitting. Is you have to go for smaller weights, you will get simpler models and it will avoid overfitting. That is number one. And like number two is very obvious. Like in L1 and L2, we add a regularization term along with the loss function to obtain the cost function. So regularization means what? Whatever is your original loss function, like gradient descent or like mean squared error or whatever you have, the log loss or whatever you have. In that we had an error function. We slightly modify the overall loss function, which we have to minimize. That's how we get in the optimum model. This is the summary of regularization. So now we go to the next concept of next and last concept of regularization today, which is nothing but your batch normalization. So we'll cover in next 10 and 15 minutes. So I stay 1 minute here, and I'll call out for questions if anybody has, Dr. Shailesh or anybody else.
No, okay, good.
Udesh, all okay with you?
Yes, sir.
Okay, nice. So now we come to our last technique of regularization, and this batch normalization is not only the technique of regularization, it fastens the training. Like it will make your training quicker. It will make your training to run very fast if you do this batch normalization. So batch normalization means what? Batch normalization means before inputting any input to any layer, like layer 2, suppose giving an output. Layer 2 neurons are giving output, which is an input to layer 3. So before inputting to layer 3, what we will do, we'll make all the input vectors, all the input values will make with the zero mean and unit variance. So whatever we are giving input to layer 3 is a vector, right? It is a matrix. It is a matrix of, say, so if there are 3 neurons, 4 neurons, so accordingly we have number of elements in that matrix. So in that matrix row, in that matrix column, we will do the mean 0 and unit variance as 1. So we are doing here standardization. We are doing standardization. We are making the mean 0 and variance as 1. That's what we are doing before inputting to any layer. So now you have a raw input data. You are putting it to your input layer of the neural network. So that's where also each column you will make zero mean and unit variance. And how we do that? Let us see a little bit in mathematical details. Little bit detail like if after every layer we'll put a batch normalization layer. Batch normalization layer will be put after every layer, as I have shown here. So I will show you how mathematically it is done. So first of all, we'll introduce one new concept called mini batch. Suppose you have say 1 million records in your data set. 1 million records in the data set. What will happen? For each sample or each record, loss value is calculated. And back propagation will be done only after all the 1 million records do a forward pass. So forward pass for all 1 million records will be done first. Loss will be calculated for each record, and then they will be added up, and then backward total loss will be propagated backward for updation of weights and biases. That's what is the regular process. But it is very time consuming because your number of records are very high. So an obvious wisdom from any scientist given by scientists is that divide that 1 million record into say 1,000 batches. So 1 million divided by 1,000. That many 1 million divided by 1,000. That many sample in one batch will be there. So now previously what we were doing, we were accumulating loss for all the 1 million records and then only doing back propagation. So now in this case, what I will do, for each batch, we'll accumulate the loss. For each batch, we'll accumulate the loss and do the backward propagation. So 1,000 times we'll do because we have 1,000 batches, right? So 1,000 times we'll have forward pass and backward pass. Like that we'll have. So this is called mini batch. This is called training with mini batch. And this will take up in next Saturday. We'll take this mini batch concept in next Saturday's class. But for now, it is enough that instead of accumulating loss for 1 million records and then going backwards, we divide it into 1,000 batches. 1,000 is again a hyperparameter, okay? It is a very sensitive hyperparameter. You may divide in 1,000 batches, 10,000 batches, 10 batches, 100 batches. So it is a hyperparameter for that neural network. And it affects the performance of neural network. So it is a very sensitive hyperparameter. So you say 1,000 batches we have taken empirically. For example, we have taken 1,000 batches. So for 1,000 batches, we will accumulate the loss for each record. And then for that batch, we'll do the backpropagation. So suppose we have divided 1 million records into 10,000 batches, 1,000 batches, 1 million total records divided into 1,000 batches. So forward propagation and backward propagation will do 1,000 times. So one cycle of forward propagation and backward propagation is one training cycle, right? One training epoch. One forward and one backward. This complete pass is one training epoch. So we'll do like that. For every batch, we will do once. So now this kind of batch normalization which we are discussing is done for every batch. At the batch level, it is done. Okay. So for a batch level, it is done. So suppose each batch is taken as a separate input. Each batch is taken as a separate input. And suppose you have divided 1 million records, total records into 1,000 batches. So we'll do batch normalization 1,000 times because it is done once for a batch. So now we'll do, see now let us, each batch is a separate input, right? So now we are dealing with batch number 1. So in batch number 1, suppose there are 10,000 records. In batch number 1, for example, there are 10,000 records. Assume that. Now what we'll do, for that 10,000 records, so it is given mathematically here. See, don't get carried away by the mathematics. It is very simple. See the right hand side box. So your batch B, your X is your input, and mini batch B. Mini batch is called B. So your X is from 1 to M. So we are telling 10,000 records are there, means value of M will be 10,000. Value of M will be 10,000. So X1 to X 10,000, we have number of inputs in the mini batch. What we do, first we calculate calculate the mean of the mini batch. Very simple. Sum up all the inputs and divided by the total number of input. Simple average we calculate for the mini batch. That is mini batch mean. It is called mu B. Then we calculate the simple mini batch variance. Variance is a standard statistical formula. So that input minus the mean whole square taken over sigma taken over all the points and again divided by the total number of records. Like M is 10,000, so M it will be divided by 10,000. So we calculate mean and mini batch variance. Very simple. All are numbers, all are continuous numbers, floating point numbers in decimals. So we can calculate mean and variance. Any problem, Dr. Shailesh here?
No, I think okay.
It is very simple, right? We calculate the mean and then we calculate the variance of that mini batch. So if there are 10,000 records in that mini batch, value of M will be 10,000. So we did that. So now we have value of mu B and sigma B square. Sigma B square we have, and then mu B also we have. Then we see how we normalize. You see the last but one formula, xi cap equal to xi means input variable minus mu B means which is the nothing but the mean of that batch divided by sigma B means which is your variance, sigma B square is your variance plus error term. We don't have to do it anytime. All computer will do in the backend. Just for mathematical understanding and developing more understanding, we are doing it. Okay, so some error term is added up. So we have done the normalization in the last but one step. Now you will ask me, sir, what is the last equation, which is y I equal to gamma xi cap plus beta. So gamma xi cap. So now if you see on the top, there is the output. Output is given on the top. You see output, input is given, and output also is given. So output yi is a function of batch normalization or gamma and beta. So what is gamma and beta? So gamma and beta here are learnable parameters which we pass from outside. So why we pass from outside? Suppose we cannot make the mean as 0 and standard deviation as or variance as 1. If it is very difficult to make for that data. So in such a case, we will provide gamma and beta from outside. So I'll show you how exactly it works. So I want to show you. This is not working. So I'll stop share. I will share again because that was not exiting. So I'll share once again. So you can, I'm not sure how to exit this. Stop share. Then PPT. Yeah, so now it has come out. So I will share again. Share the screen again. And then I'll show you this particular implementation here. So one website I found towardsdataset.com, and it is given a very nice article on how to implement batch normalization. So here, I'll make a zoom. So these beta and gamma, which I showed you, external parameters. So it is a batch normalization function. It is doing batch normalization forward pass. It is a function it is writing. We don't have to get into detail of how function is written. I just want to show the parameters. So gamma and beta is passing as outside parameters. So they are learnable parameters. Is passing from outside. We don't have to do all of this. It is just for understanding. So these are learnable parameters which are being passed from outside. And when he does all the normalization here out, then he does catch. You see catch, CSH, which I highlighted. Normalized data into, then he takes it, and then he normalizes with the help of gamma and see here out. He sees this equation which I have highlighted. So he is using gamma and beta which are supplied from outside. First he has done the normalization, which whatever formula we have discussed. Same normalization he has done. And the same normalization he has multiplied with gamma and then beta. So beyond this mathematics, we are not getting into what is beta, what is gamma, just for understanding, just for little more depth and more understanding, I told you. So one is scale parameter and one is something called, one is scale parameter and one is something, other parameter. So both are learnable parameters. And it is used when you are bringing the data to mean equal to 0 and standard deviation and 1, when it is very difficult to do that. So in that case, we use this kind of gamma and beta, but we are not going beyond this. So let us stop here. Okay. So this is batch normalization. So batch normalization is nothing but we bring all the vectors, all vector columns to mean is 0 and standard deviation is 1. That's what we do in our standard scalar in our machine learning also, right? Same thing it is being done here. And this is the mathematical process of your normalization, batch normalization, okay? And we don't have to worry because any of these things we don't have to do. All things will be done automatically by your backend process, which you have to use the procedure. But just to get a better understanding, because we are math students, a little bit maths background I have given, which I could get from a reasonable search. So at first you remember it is done for a batch. For every batch it is done once. And then what we do? That vector, whatever we are passing, its mean we make it as 0 and standard deviation is 1. That's what we are doing using that. Now how it works? See, now I have explained you all that mathematics behind this. So this slide I think already covered. So now you would like to see first like how batch normalization is used. I have not included here the piece of code how it is used, but it is very simple. Just like a dropout layer, you use a batch normalization layer after every output. You put a batch normalization. Just a piece of code, just a piece of function callout, just like your dropout.
We just have to type batch normalization and add those parentheses. That's all.
Yeah, that's it. You don't have to even pass any hyperparameter. So it's very simple. Use dropout and use after dropout call batch normalization. So that code I'll explain you when we're doing hands-on class. So that time I will explain that time of code. So now, what are the advantages of batch normalization? Number one, it makes your training very quicker. It takes your training very quicker. And generally in neural networks, whenever you input any data to input layer, it is a standard practice to scale it. You have to scale it to a standard scale. Suppose you have 10 features and all the 10 features, suppose they are on different scale. So you do apply some kind of scaler before you putting the data into neural input layer. So that is a standard practice. What is the advantage? It makes training quicker and faster. You reach convergence very fast by use. And this is why this happens. Nobody knows. Very little is known about why standardization before input. Why standardization of data before input makes training faster or convergent faster. Very little is known about why it happens, but it happens. So always do some scalar, standard scalar or min-max scalar before putting your data into input layer of any neural network. That is one thing. So now, what happens? Suppose all your data is suppose you don't scale it up. One feature is in the scale of 10, multiples of 10, and another feature is multiple of 10,000. What will happen? The weight updation when we calculate the feature, when we calculate gradient with respect to feature 1, which is in multiples of 10, weight updation will be small. And when we calculate gradient in terms of feature which is a very high magnitude in terms of 10,000, multiples of 10,000, weight updation will be more. So uneven weight updation will be there during the backpropagation process. So this will destabilize the overall backpropagation. So it is always advisable you bring all the parameters into same scale. That's why batch normalization works. So I give you an example. Suppose one feature is on a small scale. For that, gradient update will be small. One feature is on a bigger scale on thousands of 10,000s of values, magnitude. For that, weight updation will be bigger, the gradient will be bigger. So weight updates will be bigger. So this will destabilize. So in using batch normalization, what we do, we simply bring everything on the same scale. What same scale? Mean of that vector is 0 and standard deviation is 1. That is nothing but standard scalar, which we use in machine learning also. That's how, and that is how your batch normalization makes effective. I'll give you one graph here, which I have here. This graph I wanted to show you. See this graph. See, blue, simple, there are two features. One feature is plotted along x-axis and one feature is plotted along y-axis. Now these blue dots are clusters of these two clusters. When these clusters are formed, when we don't scale the features, we not scale the features before scaling. So before scaling, these are the clusters formed. But once we do scaling, say with batch normalization, if you do scaling, so all are uniformly centered around 0. and it is a homogeneous cluster. So this is the idea behind doing batch normalization. So advantage is it makes your training faster, and it helps in avoiding overfitting, but it is not guaranteed 100%. Batch normalization reduces overfitting, but it is not 100% guaranteed. So if you want to have 100% guarantee of reducing overfitting, use the dropout. Use dropout. That is the best method to go with neural networks. Batch normalization, it will reduce the weights. It will make the training faster. It will reduce the overfitting, but it is not 100% guarantee. It is one of the tool which can reduce overfitting, but not 100% guarantee. So that's how it works. And why batch normalization works and why batch normalization reduces overfitting, I think still our state-of-the-art research, people don't know much about it. There is no much theory or much concrete mathematical proof which has been developed that why batch normalization works. But in case of neural network, batch normalization does the magic. It is almost like a magic. It does the magic. It works. It does the magic. So it works. It works. That's why we use it. We are not bothered whether how it works. We are not bothered. We should be bothered. But if people don't know about it, mathematics and scientists don't know it, we also don't bother as practitioners. We also don't bother. We will also use it just like that, and we'll take out our results. And when any research comes out, and if it does any more better findings for us, so we'll use those better findings that time. For now, use batch normalization as it is. It is a way to reduce overfitting. And almost in all the cases, you must use batch normalization in all your neural networks. It is a kind of must to use neural network in all the neural networks with batch normalization, and you should do scaling of your features before putting into input layer of neural network. That also is a kind of must if you want faster convergence and consistent results. That is how it is. And I don't think after that we are, now we are left with a couple of like this is a simple training graph. Like if your batch, like your features are scaled in multiples of 10,000s or some very big features are in very big magnitude, then the step size will be large. So you can simply from right hand side, suppose you are coming from right hand side here, coming down. Instead of sliding down to local minima, your step size is so big that you are going to the left hand slide of that. You are jumping the local minima. You are jumping the global minima. And from instead of going down, you are directly going to the other side of curve. So that is the disadvantages of not scaling the features or having features on a larger scale. So this is what pictorial representation. So before batch normalization, this is the scene which is shown on the left hand side, and after batch normalization, see somewhat your curves are better. So that's it. That is one pictorial. And now another pictorial which I have included is for training curves. So take a couple of minutes and study these training curves. Actually, these are self-explanatory. I'll give you a couple of minutes. So one is, these are train and valid. Validation means test data. So two sets are plotted. Before no batch normalization and with batch normalization, with and without batch normalization. So first have a look. Instead of me explaining, you have a look which is better. Which is better? So red dots which is coming downmost, it is with batch normalization. Red dot which is coming, it is the with batch normalization. With batch normalization, solid curve, no? So this solid zigzag curve, red one, is with batch normalization, testing data, and red one below is training data with batch normalization. So train and test are somewhat better result. You see the better results. Red curves are showing better results, right? Less error compared to blue ones. So blue curves are without batch normalization, both train and test. So solid curve is dotted curve is train, and blue are without normalization, and red is with normalization. So red curve is below. So we are plotting a misclassification on misclassification percentage. We are plotting on x-axis, y-axis. So you see the better. We see slightly better results with red ones with batch normalization. With blue ones, you have some values, but it is above red one, right? Both training and testing are above corresponding curves. With red ones, you get the better result. Do you agree? Dr. Shailesh, do you see that?
Yes, yeah.
Someone, you see that?
Yes, sir.
With red ones, you have better results. So this plot I have taken from such paper just to demonstrate you what is the effect of batch normalization in overfitting. So we are getting better results with batch normalization. So if you are getting better result, just add one simple line of code without any hyperparameter. Why not use it? Use it.
But in Dropout, we are using some
hyperparameter. There is a hyperparameter.
So here we are not using any parameter.
No parameter. Simple batch normalization. Just a piece of line of code.
Call the function and that's it.
Yeah, we call a function with simple empty brackets.
Okay.
I'll explain at the time of coding when we'll do coding class. So that time we'll use with bracket. So now I think that's what I had planned, and I think in reasonable time we have finished again in 1 hour 10 minutes or something. So I think I planned that much, and we completed the regularization in very great detail today. And all the aspects we have taken up, which is required for you to code or to discharge your duties in your respective organizations. I don't think more than this you need it. So with this, if any questions, I'll stop for a minute. Else, we'll say goodbye.
One question actually for this for CNN, we have already scaled all those images, BGY, green.
Yeah. So all the pixels are on 0 to 255 scale, na?
Yeah. So
just divide it by 255, it will be scaled.
So that is the scaling which we are talking about.
That is the scaling we do.
And
just divide all the pixels by 255. That's all.
Yeah. So on the top of that, do we have to do this batch normalization, or once we have scaled?
No, see that input will come, pixel input will come only on the input layer.
Okay.
Whatever output layer comes from the first hidden layer, there will be output, right? That will not be normalized. So that also you have to normalize before putting to the second layer.
No, but that will always be between 0.
No, not guaranteed. Not guaranteed. You are doing a lot of operations. You are doing pooling, you are doing convolution, you are multiplying by weights, you are adding biases. So you cannot guarantee that these numbers after coming out, which are coming out of layer 1, will be between 0 and 1. You cannot guarantee that. It may be very high in magnitude. You don't have any control on that.
Okay. So
that's why you have to apply after every hidden layer. You have to apply batch normalization.
Okay. And one last question.
After every layer, you have to do like any input to the next layer should go only after batch normalization. That's what is the science.
So is it valid for this RNN? I think
everything, all neural networks.
RNN also.
Everything, all neural networks, it is valid.
Okay.
This phenomena is valid for all neural networks. All these regularization concepts which we studied today are across ANN, RNN, CNN.